Okay, so first one that I want to look at with you guys is the following. Let's imagine that we are talking about a rocket. And so, a little bit of a big rocket there. We're going to go ahead and start. This is the initial situation. We're going to start on the ground at rest. Let me make sure that I am recording here, because sometimes I think I'm recording and I'm not. Yeah, I am recording. Okay, so we're at rest, we're on the ground, and let's go ahead and do this in terms of this being a 1,000 kilogram rocket. All right, and let's go ahead and put this thing, we fire the rocket off. All right, and so as it travels upward, all right, it's going to encounters a 500 Newton air resistance force. And the other thing that we have is obviously when this rocket fires, it's going to be providing a helping force that's making the rocket move. So not only is it encountering a 500 Newton air resistance force as it shoots upward, we're going to also say that the rocket exerts a 1,200 Newton force of propulsion, pushing the rocket ever higher and higher. So here is the question. We would like to know when this rocket has reached a height of 600 meters. All right, so the rocket is now up here. I want to figure out how fast is this thing going? That's what I want to do. So this is our initial situation. This is what it's encountering, and this is the final situation. So at this point, I'm just going to kind of do a quick check-in and see who I see here. Just seeing if anybody joined us. All right. So good morning, Aiden Bailey. I think you're getting on there here. Welcome. All right, so let's do this. Let me get back to making that small. Hey, Ben, if you can unmute there, I'm going to ask you a couple questions.
Yeah.
We've got clearly a situation where we've got some work and some energy. So total initial energy plus work equals total final energy. What type or types of energy should we write here at the beginning?
Gravitational and potential.
Okay. Tell me why you're saying both here at the beginning when it's on the ground at rest.
Because it still has gravity pushing down on it, and then potential because it's at rest. So,
Okay. All right. Let me step back for a second. What is the formula for gravitational potential energy, Ben?
mgh,
And what is the formula for kinetic energy?
half mv squared.
Okay. So if we're going to say that it has kinetic energy, what does it have to have?
The velocity.
Is it moving yet at the
No.
beginning? No. So it's got no kinetic energy.
So it's just gravitation.
And what's its height?
0.
So how much gravitational potential energy does it have?
None.
So let's revise our answer. How much energy does it have at the beginning, Ben?
0.
None. Does that make sense?
Yeah.
Okay. Annie Brickley. Thanks, Ben. Annie, if you don't mind unmuting there, let's think about the work terms. Do you remember what we said the formula for work was?
No, I don't remember.
That's okay. Let me chime in, anybody, and just kind of identify yourself. What's the formula for work? We'll come back to you, Annie.
Force times distance?
All right, Anna, thank you very much. We got force times distance, all right? So Annie, we've got two forces acting on this rocket. We've got a 500 Newton air resistance force, and we've got a 1,200 Newton force of propulsion. Let's deal with the 1,200 Newton force of propulsion first. Annie, is this rocket putting energy in or taking energy out of the rocket?
Putting energy in.
Yeah, because it's making it go faster, all right? So we're gonna put plus, and we always put a plus sign. And since we're adding energy, it's gonna be a helping force times the distance. So Annie, what force should I put here if we're focusing on the propulsion side of things?
1,200
Uh-huh.
times 600.
Perfect. So what we're doing is we're taking into account, this is the work done by the engine. So I could write that as work engine. All right. And let me see here. I think Anna, thank you, Annie. Anna, let's go now and think about what should we write for the work term for the air resistance. Is air resistance putting energy in or taking it out, Anna?
It's taking out, so you should do negative 500 times 600.
Bingo. We've got to take a hindering force of 500 newtons, because that's the resistance. And then you said multiply it by what?
600?
600 meters. So we have, in this case, two work terms. This would be the work done by AR, air resistance. All right, let's go over to Addie. Addie, what we've got our no energy to begin with. The engine puts work in, the air resistance takes work out. What type or types of energy do we have at the end when we're up here?
We have potential energy.
I totally agree. So UGF and anything
And,
else? Would it have
kinetic energy as well.
Why does it also have kinetic energy there, Addie? What is it?
Because it
Yeah, go ahead.
it's moving.
Yep. And that's all you
Yeah.
have to say. As long as it's moving, as long as it has velocity, it's going to have kinetic energy, okay? Now, you guys double check me here. Holler if I do. Ooh, not sure what I just did there. I'm going to get my calculator out. That's going to be 1200 times 6. I think that's 72 with 4 zeros. Can I get a confirmation on that number? Anybody can just kind of say, yep, you're right there, Mr. Caldwell.
That is correct.
All right. And then I'm going to do 500 times 600. And I'm not done writing, but I just wanted to go ahead and do some math. And I'm thinking that that's 1, 2, 3. Oh dear, have I screwed this up? 1, 2, 3, 4, 5. I don't think so. 3, 4, 5. So if I take that and I subtract those two numbers, double check me. Does that look like 420,000 joules? I think that's
Yes.
right. Okay. Now let's go back here, and I'm trying to remember who else I've got. Is let's see. I think, did I have Aiden? No, who is it? Yeah, Aiden. Aiden, help me out here. Do you remember we've got the formula for potential energy over here? So what should we put as the potential energy 600 meters up here, 1,000 kilogram rocket? What's this term going to look like, Aiden?
Wait, which one's the formula for potential energy?
Right over here. So we got the MGH, and you guys can see that, right? My calculator wasn't in the way. Okay. So MGH. So what did we say the mass was there, Aiden?
Um,
I'll give you a hint.
I'm not sure.
Okay. Yeah.
1,000
Oh yeah, because
kilograms.
you were catching up, man, because you came
Yeah.
in just a little late. Totally apologize. So we're gonna go with a mass of 1,000. You remember what G stood for, Aiden?
No.
It's the acceleration of gravity, and that's 9.8 meters per second squared. And then H is height.
600.
We're gonna go with 600 there. All right. Now I'm hoping that I haven't made a problem that is impossible to solve. I'm looking at these numbers and they're starting to get me a little bit sketched out. So if I do this, 1,000 times 600 times 9.8, oh dear. Oh dear, oh dear, oh dear. Let's just 588, 1, 2, 3, 4. Oh, I think I've completely bungled this up. Because look at this. This is how much energy I have, 420,000. And this is telling me that I have to have 5.88 million. So here's the beauty of this. All right, we're doing this live and Mr. Caldwell didn't check his numbers beforehand. We're going to go ahead and we're just going to say, okay, this would be 1/2 times 1,000, and we would do V squared. And because Mr. Caldwell is a moron, we're going to laugh and we're going to say, if I subtract that over, that would give me a negative quantity. And then I would be basically saying, hey, I've got a V squared of a negative thing. And I'm going to put a big frowny face here. And I'm going to be sad. Here's a little tear because I gave you numbers that don't make any sense. So I'm going to blame all of this on me and the fact that it's Monday morning. But here's the important thing. I'm going to go ahead and stop sharing the screen so we can all look at each other. Yeah, so totally my fault. Okay, I screwed that up. I'm going to pause the recording. Okay, so let's do this. Let's imagine that we are in an airplane and we are a parachutist. This is clearly not drawn to scale because the person is too big for the airplane. And so we are going to assume that we are at a height of 1,000 meters. And yes, we have a horizontal velocity, all right? But just to make the problem easier, why don't we go ahead and just pretend as if this person has no velocity, all right? Because really he's not going up or down, he is just going horizontally. So we're just gonna assume that we're at rest 1,000 meters up. The person is gonna definitely encounter air resistance as we fall. And let's just assume that that air resistance is a 100 Newton force. And so the question that we want to ask ourselves is this: when the person who is here and is clearly falling, looks like his arm got broken there, that looks tragic, I want to figure out how fast are we going at a height of 200 meters here. All right, so this is our initial situation. This is our final situation. And so in between the height of 1,000 and the height of 200, we've experienced an air resistance force of 100 newtons. I'm going to just pause my talking for a second and give you a chance to write out what you think the energy equation would look like.
Do we know his mass?
Let's go ahead and, yeah, let's make the mass 50 kilograms. And then I'll maybe get somebody to share their thoughts in a moment. Okay. Let's go ahead and start out there with, oh gosh, I don't know who I've neglected. Maybe Jennifer Overdahl, if you don't mind sharing what your thoughts are so far. What do we have energy-wise at the beginning?
We have potential energy and work, obviously.
Okay. We got potential energy and work. And then what types of energy do we have at the end?
I said that we had both kinetic and potential.
All right. I think that that's on an absolutely great track. So thank you very much. Let's go over here and look at Kate Schwab. Kate, do you mind kind of filling these in with some numbers? What would we put for the UG, the potential at the beginning?
50 times 9.8 times 1,000.
50 times 9.8 times 1,000. All right, that looks pretty good. And then go ahead and give us what you think the work term would look like there.
I'm not really sure on this one, but I said plus a negative 100 because I don't know where else the air resistance goes, but I don't know if that's right.
So let's think about this. Is this a helping force or a hindering force for the motion of this guy who's falling?
Helping?
Is air resistance helping him go down, or is it resisting him going down?
I thought it resisted things going up, so that's why I'm thinking helping now. But does it
And
resist both
no,
ways?
no, don't talk yourself out of the right answer. You're totally right. I just wanted to make sure you understood why you were right. It should be negative because it is resisting the motion. Now, over what distance does that resistance force act? If I started at a height of 1,000 and I'm now at a height of 200 meters, how far have I fallen, Kate?
800.
Yeah, so it's a little bit sneaky there, but we actually do know the distance. Does that make sense, Kate?
Yes.
Okay. All right, so let's go over to Anna. Anna, what about the kinetic energy and the potential at the end? What should we write?
For potential energy, you should have 50 times 9.8 times 200.
Okay, because we are at a height of 200 meters right here at the end. And what about the K?
1/2 times 50 times v squared.
Beautiful. Let me go and look at all of you guys. Give me a thumbs up either for real or virtually if that makes good sense to you. All right, cool. So look, the rest of this is math, all right? And I'm just gonna trust that we do the math correctly here. We could all sit here and crunch it. If we wanna take a couple moments to make sure that we're all doing this right, we totally can. I think what I'll do is pause the recording. So here's the thing, guys. It's not like I've taught you anything new from what we were doing towards the end of last week. We're just getting a little bit better at it, just doing some more practice with it. And that's literally, that's what we're gonna be working on this week. It's just taking wherever we are and getting really comfortable with these things. So I'm gonna go ahead and stop the recording unless you got a question about something.